So I'm Dominique Devriese, so you were not that far, so that's I've had French people pronounce it as Devriese, so that's maybe more creative but less accurate. I want to tell you about a project that I've been working on with collaborators for a few years already, and it's about the security properties of ISAs. So we want to look into specifying them, verifying them, and applying them in reasoning. So the starting point for this work was sort of the observation that ISA specifications traditionally have been written as sort of prose, as big piles of books of thousands of pages describing in sort of prose and sometimes a bit formal with tables and stuff how the architecture is supposed to work, and these books contain a functional spec for the ISA, but they also contain other properties. They contain statements of security guarantees, and particularly I will talk a bit more about what I mean with that, but you should imagine things like when a kernel invokes user codes, it sets up the CPU in user mode, it sets up the page tables in a certain way, etc., etc. And from that, it can sort of derive, it can sort of rely on the fact that the user mode code is going to be able to do certain things and not be able to do certain other things. That's a security property. That's sort of a meta property about the semantics of the ISA. And we've had a few talks already about formalizing ISA specs. Of course, having ISA specs in prose, in English language books, is suboptimal for various reasons. There's a lot of work, and even industrial companies are starting to take that seriously more and more on formalizing these specs. Often what this looks like, or what you should imagine, is sort of a definitional interpreter for the ISA, often written in a well-designed domain-specific language for doing that. Like we've had talk about SEO, that's one of the main contenders in that space, let's say. So we have this sort of formal version of the functional spec, but what's still missing is a formal version of the security guarantees. And the formal specs do not contain that in a sort of explicit way. So to make this more concrete, the kinds of security properties that I have in mind, I've already mentioned one. When the kernel invokes user codes, the kernel should be able to rely on the fact that this user mode code is only going to be able to access memory through the page tables. It's not going to be able to access certain peripherals directly unless that is allowed by the kernel, etc. And ISAs come with many security primitives that are in a way of a similar form. Hypervisors can pass control to virtual machines. In trusted execution, confidential computing, you can have enclaves that pass control to non-enclave codes, but rely on the fact that non-enclave code will not be able to access their internals in certain ways, under certain assumptions. On the capability machine, we've had the talk by Angus and Thomas and Brian. When code passes control to other codes, but only gives it access to certain capabilities, then the code has certain expectations about what the invoked code will be able to do and what it will not be able to do. And what's important is that these properties are not just sort of like lemmas that happen to hold about the current semantics of the current instructions in the ISAs, but they should also be something that you can rely on in future versions of the ISA. When all of these properties, when Intel comes up with a new extension of their ISA, we shouldn't have to fear that suddenly user mode code is going to be able to access things that it previously wasn't able to access, right? So these security properties are sort of meta theorems about the ISA semantics that should be considered as part of the contract and not just lemmas that we use for proving stuff about one version of the contract. So in this project, we've been trying to work out a sort of general way to try and specify these things. How can we add something, some kind of specification to the ISA to express these security guarantees in a general way, so that we can use them. We can use them for reasoning about codes. We can verify that they actually hold in a certain version of the ISA, that they still hold when you make an extension of the ISA, etc. And our starting point for this was the question, how would we like to reason about trusted code that makes use of a certain security primitive? So suppose we have some, suppose we have some system composed of some small bits of trusted code, and maybe these green bits have somehow have exclusive access to a peripheral, and they encapsulate a big untrusted system, but prevent it using some ISA security primitive from accessing those peripherals directly. So the untrusted code is somehow forced to call back to the trusted code in order to do that. How can we then reason about this system? How can we then reason about the combined system and somehow derive properties about the interactions that the system as a whole can have with these protected peripherals? And we've been looking at verification. So we can verify those trusted bits. We can use OR logics and separation logics and symbolic execution and so on, pre and post conditions. We can verify those parts. We can sort of give specs to all the components here and verify them. But it was unclear to us, at least in the beginning, how we want to verify about these parts. So how can you reason about code that you do not trust, code that you do not know? So it's sort of unknown code. First, what contract can you give to that code? And second, if you even had a contract, how could you reason about it? The sort of central premise of this work is that we want to be able to nevertheless give a contract to this code. So we want to come up with a contract that somehow holds for arbitrary code, for untrusted code. And it will say things like, the contract will express the security guarantee that you have when you invoke untrusted code in a certain properly set up way where you properly set up certain security primitives. So essentially, for a sort of arbitrary security primitive, you would get a contract that says, if you set up the security primitive correct, so that you specify what the untrusted code should have access to and what it shouldn't have access to, then the untrusted code will respect that authority bound, let's say, and afterwards it will only be able to jump back to the trusted code at certain entry points, for example, interrupt handlers or object capabilities, etc. So we can come up with this sort of what we call a universal contract. So the universal in the sense that it applies to arbitrary code. In many ways, this is sort of, or I see it as the same thing as a free theorem that you have in System F. You have a sort of theorem that automatically applies to all values of a certain type. Here we have a sort of contract that automatically applies to all code that you can write in a certain assembly language. So we can specify such a contract, but even then, can we be sure that it holds? Also, I want to say this idea of universal contracts, it's not sort of in itself a novel thing. This is sort of, many people have done similar things, but this is sort of, I'm sort of highlighting this because it's sort of a central premise in this work. Now that we have this arbitrary contract, this universal contract for arbitrary code, we can actually also verify it by checking that the functional spec of the ISA actually validates this contract, that we can check in the specification of all the instructions whether all those instructions actually do the necessary checks for our security primitives. And once we have verified the universal contract, we can use the universal contract at those points where the trusted code invokes the untrusted code. And then the trusted code, that will force us to check that the trusted code sets up the security primitives correctly and that the assumptions it then makes about this invocation are actually correspond to what the hardware actually gives you. So universal contracts, our idea is that these statements of universal contracts should be regarded as a statement of the security guarantee that an ISA gives you and considered as part of the hardware-software contract that the ISA is. And that means we have the same requirements as you always have when you define a hardware-software contract. When you define an ISA, it should sort of satisfy both the design goals of ISA designers, but also the design goals of software developers. And in both cases, both types of people want this type of spec to be unambiguous, so we want something formal. ISA designers like it if the spec can remain maximally abstract. They still want to be able to do clever things when designing hardware. And they need to be able to verify that the contract still holds when they make changes to the ISA. And at the same time, software developers need a spec that is precise enough for verifying software that relies on that makes use of security primitives, and that is sort of hardware agnostic to a certain extent. It shouldn't just hold for one specific version of a specific processor, but maybe a family of processors or sort of a generation of a certain processor. And second, the spec should be precise enough that you can use it for verifying trusted software. And both of these are the sort of the requirements that we've been trying to reconcile in this project. So in this talk, what we might talk about, first I will tell you about Katamaran. This is a verification tool that we built for sale. It's a bit similar to tools like Viper or VeryFast or those kinds of verification tools, Y3 to a certain extent maybe. So it's sort of a verification tool, except it's not for C or for Rust or for whatever. It's a verification tool for sale. It's a verified verification tool, so I will tell you more about what that means. Second, I will tell you a bit about universal contracts, specifically 2 case studies that we have looked at, where we have tried to realize this idea of universal contract as sort of the extension of the hardware-software contract with security guarantees. I will try to tell you about how we verify them against the ISA spec, and how we use the universal contract for reasoning about trusted code, and then finally offer some conclusions, tell you a bit about next steps that we're looking at. So first, Katamaran. So Katamaran is a verified semi-automatic separation logic verifier for sale, and it is implemented and verified in COC. So this is quite a big artifact, let's say. It works by, it starts from, so it starts from the specification of your ISA, which consists of function definitions, but also you need foreign functions. Often you have custom data types, etc. So all of these are provided as input. Additionally, you can provide extra inputs like certain lemma statements. You need to give contracts for foreign functions, etc. So you provide both the spec you want to reason about and certain extra annotations to help the tool reason about the code. And then the tool will run a symbolic executor on the code, which may result in remaining verification conditions. The whole tool is proven sound in sort of a sequence of proof steps. So the symbolic executor is proven sound against the program logic, sort of an axiomatic program logic. We have one instance of that axiomatic program logic built on Iris, and the Iris model is itself proven sound against an operational semantics for sale, let's say. Sometimes you need to prove these, you have some remaining verification conditions that you still need to prove at the end, and there's also, when you've used lemmas, you also need to prove separately outside of Katamaran that these lemmas are actually sensible, that they actually hold. Okay, so I'm a bit confused about my presentation. So let me try and give you an idea of what this looks like in practice. So this is a sort of representative function in a sales spec. It's actually not SAO, it's microsale, and microsale is sort of our core language that we translate SAO to. It's part of a capability machine ISA spec. So what you have here is it's the execution of a store instruction, which has two arguments, which are names of registers, and there's an immediate. And what the code does is it will read a capability from the second register. It will deconstruct it into its parts, add the immediate to the cursor, read the second register, write the word that's read from the second register to memory in this at the location pointed to by this modified capability, update the PC, and then return. And you see here that we have a lemma that is used to help Katamaran in verifying this. We provide a contract for this. In this case, it says that the PC is expected to point to some capability, and that capability should be valid. I'm not going to go into full details about what that means, but it's actually sort of the same definition as what is used in Cerise, and I expect in Cerise Morago as well. And the same should be true for all the general purpose registers. Okay. What Katamaran will then do is it will start from this precondition and sort of step through symbolically through this function and sort of compute intermediate assertions. This is what symbolic execution-based verifiers do. As an example, I show what happens here with this lemma. So here we have some knowledge about the current value of the things that have been computed here. We know that this base cap is valid, but we actually need to know for that call write mem, we need to know that this computed capability C is valid. And for that, we use a lemma that establishes this, that when you change just the cursor, that the capability remains valid. And you see that Katamaran will take the hint and actually know that the capability is valid and can then continue. Okay. Here, in this version, it's still, you need to manually invoke this lemma. We have some work on heuristic that would automatically, or we want to get to a point where we can register a heuristic that will tell Katamaran to always apply this lemma in this situation. But that's not yet in this version, yes.
So how do you instantiate these existential quantifiers?
So good question. So Katamaran has a quite nice system for dealing with logical metavariables. So you can it uses angelic and demonic non-determinism, like one of the speakers yesterday mentioned. So what you will get when you invoke this, so when this function is invoked, Katamaran will try to instantiate the contract for you based on the sort of assumptions you have available. It will then, when it sees that it requires an existentially quantified assertion here, it will create a fresh meta variable for this C, and then it will try to satisfy this precondition for that meta variable from the assumptions you have available. In typical cases, that will sort of, you will only have one choice available, and that will allow Katamaran to instantiate the meta variable with the value that it should have. So this is this works quite well. This works the same way as it works in many other similar verification engines. I don't know if this answers your question. It's, in a way, it's the same kind of meta variables as you have in type inferencers, like in algorithm W but okay. So, but I won't go into full details about these kinds of things because of time constraints. So that's a bit of the, let's say, the goal of Katamaran. I won't go into full details about how everything works, but I want to mention a few points. First, yeah. So first, Katamaran doesn't actually consume sail code, it consumes microsail. That's our sort of core language for sail. We can translate sail into microsail. Currently, we have been doing that manually, but we have a tool, a sort of new backend for the sail compiler that's, I hope, 90% ready for doing this translation automatically, and then we should have more access to other ISAM models. You want to ask your question now, or? I can. It's about. Okay, yeah. So second, Katamaran works with specifications in separation logic. It can take a significant subset of separation logic. However, the automatic reasoning is, of course, limited. It won't automatically apply magic wands and stuff, but the basic separation logic arguments are largely automatic. It uses symbolic execution, like many other tools. Katamaran comes with many extensibility hooks. You can define custom data types, both logical ones and the ones that you need in your actual ISA spec. You can define custom logical functions. You can register custom predicates. You can register lemmas. There is some support already for heuristics, but we hope to improve that further. An important or a sort of special characteristic of Katamaran is that it is not implemented in LTEC like many other tools, but it's implemented in Galena. So that means it's sort of fully. The tool is implemented in the same way as you would implement it if you build something in OCaml, for example. Except we have sort of separate cock proofs about it that say that. That it actually is sound, and that when the tool says this contract is valid, that actually holds with respect to the iris model and the operational semantics. The fact that it's implemented in Galena has certain advantages, although you can maybe debate about how useful that is. One advantage is efficiency, so we think verification should in principle go faster in this way than if you run it in LTEC. Second, we think, our Galena is in principle extractable to languages like OCaml, JavaScript. Maybe that's what your question was about.
That was the main question, yeah. Because I read the ICT paper and I was very if you extracted it or not.
So we aren't doing that yet. I think we experimented with it at some point, but that was sort of an experiment. But in principle, it should be possible. We hope to use that to connect the extracted code to some GUI, maybe a language server for, I don't know, Visual Studio or whatever, so that we can put a nice GUI in front of the verification engine. But that's not there yet. Yes.
But take a look at your previous slide. It looks very much like shallow code. So you're using the fault binders and where the things in the pre-post conditions just refer to the binders themselves.
So it's not actually shallow code. It's not actually a shallow encoding. It's a deep encoding, but my postdoc Steven Koicho likes to play with fancy cock notations. But this is a...
Get the binding? Yeah.
Which
What
binding?
do you use for binding? How are the lets represented? What is the W?
It's the Bruin variables, etc., etc. But
How do you get it to look like a normal goblet?
So first, I'm not the expert there. I think we should take this offline. I can look at the code and try to show you. But if you have deep questions about how my postdoc plays with these cock notations, I'm going to have to refer you to him.
Looks like something magic.
It's also, so this is also code that I stole from a previous presentation by my PhD student who did some work here. It's also possible that this has been made a bit nicer for the presentation. But I'd have to check. Okay, but the main point is we are using a deep embedding of the SAIL, of the micro SAIL code. The soundness proof proceeds in a number of steps. First, we have this symbolic executor, which is proven sound against a shallow executor. A shallow executor, you should imagine a weakest precondition predicate transformer semantics that is shallowly embedded rather than deeply. That is proven sound against an axiomatic Hoare program logic, or axiomatic Hoare triples in a certain separation logic, I should say. One instance of those axioms is our iris model, which is then itself proven sound against the operational semantics using the standard iris machinery. One of the parts that I still hope that I want to mention explicitly is that first part, because we hope that we or other people might be able to do more with it than we are currently doing, namely this this symbolic executor is actually implemented in a quite nice way if you compare to some other work that we based ourselves on. So the symbolic executor really is written in a monadic style where you match, here there's a match on the microsale statement, and then for all statements it returns sort of a logical representation of the result value, and then also modifies the symbolic state in a certain way. But all of this is done in a relatively brief monadic style. There's one bit of syntactic overhead there with these omega terms. Those are sort of witnesses of the substitutions that happen with the meta variables. But to a first approximation, you can just ignore those, and then you have a symbolic executor written in a nice monadic style. The soundness of this symbolic executor is proven by relating it to a shallow executor that's written in almost exactly the same form, except that it doesn't have these substitution witnesses and is also has a simpler type, but I'm not going to go into that. And there's a largely automatic proof that relates this symbolic executor to that shallow executor, and that's actually and I can say this because I didn't come up with this, that was my postdoc. I think this is a very nice abstract interface for writing this kind of tools. So if you ever need to write a symbolic executor and prove its sound in Coq, I think you should look at this machinery, because there's it does a lot of the clever bits for you. Next, so that's what I wanted to tell about Katamaran, and there's a lot more to tell, but that's for a different occasion. Next, I want to tell you a bit about the universal contracts that we propose. First, so we've done 2 case studies. The first case study is something we call minimal caps. It's roughly modeled after cherry risk 5, but it's not intended to be an accurate representation of that ISA. It's more like a sort of a first testing scenario that we worked on. It has roughly the same features as Cerise. It's a bit more representative of cherry risk 5, but not entirely. And we use Katamaran to prove something that corresponds quite closely to Cerise's FTLR. Yes?
As it were, before you get into this part, can you compare the symbolic evaluator against ILA in any meaningful way?
Well, so ILA is a non-verified symbolic executor, which means you can do things that we cannot. So you can, for example, hook up to an off-the-shelf SMT solver, which means it's going to be more automated than what we do. Here we have a quite basic, so I hesitate to call it an SMT solver, but we have a quite basic equivalent, let's say, or a minimal version of what would be an SMT solver. But it doesn't always manage to solve the proof obligations you want, and sometimes needs extra help. It's also, I think it scales quite well as a Coq implemented tool. It doesn't, but I don't know yet. I don't know at this point whether it will scale to the size that ILA scales to, and probably not without extra engineering effort. That's what I would expect.
Yeah, so this is really my question: is whether this demonstrates that you need some of that untrusted stuff that ILA does in order to work on actual ARM instructions, or whether you can get it to work inside a verified world.
Yeah, so that's definitely something that's on our agenda to try. Yeah? So when we've tried, I will tell you. But the fact that we're implementing this in Coq, it slows us down to a certain extent. So at some point, I've wondered whether we should be building a non-verified version of Katamaran instead. But on the other hand, it gives us extra certainty. It gives us it's a different challenge to a certain extent, right?
You mentioned here the SMT server that you've implemented, and I'm wondering about how, but like when you do symbolic execution, there are two kinds of sign conditions you're getting. Either somewhere you know, okay, I now need to prove this assertion, and if the SMT solver can approve it automatically, you can ship it to the user to like as a verification condition generate verification condition, and that's fine. But there are also places where you need to use an SMT solver as a decision procedure, as saying like, I have this list of heap chunks, I access a certain address, which of these heap chunks does it correspond to? And there you need like a strong enough solver to be able to decide which of these.
Yes, so you cannot post, so the SMT solver during verification gets a number of, a big number of queries at certain points. In some cases, it's okay to delegate those queries to sort of the user and leave them until all the way at the end. However, in many cases, you have to solve them when you see them, because, for example, maybe it's the decision that maybe you have 10 branches, but the SMT solver will tell you that 9 of the 10 are actually bogus, and you only need to look at this one branch. If you do not solve that query at the time where you get it, then your path explosion becomes even worse than it already is in symbolic execution, and so. So that's why, indeed, this is what we do. So we try to solve simple SMT queries. I hesitate to call them SMT queries because the solver is not a general SMT solver, but the solver does solve many simple queries during symbolic execution, and that already brings down the path explosion problem to a manageable state, to a state that we can do the verification that we are doing. Yeah. Yes.
Could you try to factor the ad hoc SMT solving for a sort of clean SMT interface? Because I mean, there are people looking at verified SMT solvers, right? So you could try to have an actual like SMT lib interface, and then you would be kind of generic. Could you do that, or do you kind of depend on the specific?
We've thought about this. We haven't explored it to a significant extent. But indeed, especially when we start looking at extraction, then why not hook up to a real SMT solver, right? But we haven't investigated in detail yet. You could ask my postdoc. He sometimes looks at these things in the background and doesn't always tell me exactly what his thinking is on that front. So yeah.
And maybe another question. So you say you have this mini sail language.
Microsail.
Or microsail, whatever. How much of this depends on using microsail as opposed to proper sail?
I think the microsail has mostly technical differences with sail. There's a number of things that are really sort of real differences. For example, we currently don't have exceptions, which is a difference. I should think. We have in the paper there's a list somewhere where we try to list sort of the real differences, but most of the differences I would say are technical. For example, it has one difference also is it doesn't have a type system. So we sort of erase sail types when we go to microsail, where the assumption is that they need to be re-expressed as part of the contracts. We hope at some point to be able to do that translation from sail types to separation logic contracts as part of the translation automatically, but that's completely not there at the moment. So universal contracts. So we have these two case studies. One of them is roughly a sort of at the same level as the basic series, where we prove a very similar result as the series FTLR, and this V is a sort of faithful representation of the series logical relation. Apart from that, the contract is written in a bit of a technically different way, but that's let's say a superficial difference. A second case study that we looked at was so we wanted to demonstrate. So we wanted at the time to demonstrate that this approach generalizes, that the things that my collaborators and I have been doing on studies for a few years, that you can use a very similar approach to reason about security primitives in other types of security primitives in other ISAs as well, and particularly in realistic ISAs. To demonstrate that, the first target we looked at was RISC-V, which has a certain security primitive called PMP. So PMP is maybe the most basic security, it's sort of the most basic security primitive that you have in RISC-V. It allows machine mode to specify a policy on memory that sort of says this range is read-only for everyone, and this range is read-write-execute, but only for machine mode, and this range is executable and readable, but not writable. These kind of policies. We specify this security contract as a Hoare triple here, as a separation logic Hoare triple, which states that if you invoke the FDE cycle in a certain state of the architectural state, then the machine will respect the authority that is expressed here, and it will not use any authority that is not here. So what does this state require? It requires that you have access to all the registers and the PC and the MCAUS and so on, and certain architectural registers of the machine. It requires that you have access to the registers with the PMP policy, and this PMP policy, we call it entries here. It requires that the CPU is set up at a certain privilege level L, and then, most importantly, it requires that you have access to the memory represented by that PMP policy at this privilege level. Okay, so and given the authority for that memory and not any more authority, all other memory can sort of be framed off, and which means you get guarantees that the code will not try to access any other memory. Under those assumptions, the CPU will run correctly. There's one additional assumption, and namely that which is related to the fact that the untrusted code can jump back, right? And it can do that by invoking an interrupt handler, or in this case, for now we are only modeling synchronous interrupts, so which means syscalls essentially. And here there's an extra proof obligation. That means when you try to use this universal contract for reasoning about a jump to untrusted code, it's still your job to prove that your interrupt handler is itself safe. And that's this proof obligation, which says that if the untrusted code jumps back to you in this state, and I'm not going to go into full detail about what it is, but essentially it says the PC points to the interrupt handler you've configured here, and you will be in machine mode, and all other registers will be in an unpredictable state. So under that assumption that you can prove that your interrupt handler is safe under those assumptions, and then you can justify the jump to untrusted code. So we have verified these universal contracts against the functional spec. So that means that all the instructions, all the semantics of the instructions actually validate these security guarantees. There's some statistics here about the proof effort. So the semantics is about, for RISC-V PMP, the semantics is about 1,600 lines of code. And then there's some details here about the lines of code in the specs, the proofs, the iris model, and a custom solver that we added. Yes?
You have an estimate of how much regular sale, 1,600 lines, that 1,600 lines of microsale?
It should be the same order of, it should be on the same order, I think. Maybe a bit smaller, I don't know, but it should be the same. Microsale also has some restrictions, like it requires a certain SSA-like form and so on, so it's possible that if you write sale, that where you have less of these restrictions, that it's a bit shorter, but
not like
yeah. Yes?
You mentioned framing. How useful is the separation of the aspects? Do you imagine doing the same in a whole object?
So the separation logic, on the one hand, is important because it's because of expressiveness reasons. We don't just use a sort of Reynolds style separation logic. We use iris, which has features like invariance and different sorts of different kinds of invariance, etc., etc. So in terms of expressiveness, also the separation logic allows us to do the verification more efficiently because yeah, you can more easily frame off certain things in separation logic than you can do in other program logics.
This is maybe a question for you and Michael, whoever Michael is. Is the iris model basically the same as the one of Pilatus, or you have accuracy? Or are they interestingly different?
So I think the Ilaris model uses a very different operational semantics, right? With these traces and stuff. Am I?
The resources.
So the Alaris resources are not super fancy. I could imagine that that's very similar. So it just has like points to predicates for like registers in memory.
Yeah, the ghost state is not very fancy in our model, no. But the operational semantics in Ilaris is quite different, right? So in that sense, the model will, the iris model will be quite different. So.
And here it's just sort of a conventional operational semantics for microsale.
Yes. Yeah. Yeah. Just a small step, judgmental operational semantics. Okay. So next I want to tell you briefly about using this to verify trusted codes. And essentially we are sort of reusing a lot of the infrastructure that we had already. So I was playing a bit with a font here to suggest assembly codes. So this arcane font is supposed to represent some block of assembly. The idea for verifying trusted code is essentially an idea that we are reusing from Ilaris, and namely that if you want to verify a contract for a block of assembly, you can sort of unfold that proof obligation to a contract for the FDE cycle of the ISA spec, and namely that the FDE cycle of the ISA spec should satisfy this contract if you run it in a state where it is looking at that assembly, right? And that's sort of an idea we sort of stole from Ilaris and also implemented or re-implemented in the context of Katamaran. We call this the block verifier because it reasons at the level of basic blocks in assembly. And we can use that to verify like small amounts of code with relatively little effort in building a symbolic executor. Specifically, we do not actually build a symbolic executor for assembly. We just run the symbolic executor for sale under an assumption that it's looking at the assembly we care about, which means we get a sort of symbolic executor for an arbitrary assembly language as long as we have a sales spec for it. So that's a bit of an exaggeration, let's say, but it's relatively cheap. It has its disadvantages, of course, namely that executing one instruction means running through an entire chain of functions in the sales spec, but still, so this is I thought this was nice. We use this to verify, so one minimal example that we use to show that this works is what we call the femtokernel. So it's about 20 lines of assembly code, but it's sort of a machine mode code in RISC-V PMP that jumps to untrusted codes and has an interrupt handler for when the untrusted code jumps back, etc. And it enforces a certain policy on MMIO interactions with some peripheral. And so all of this works, and we have a full admit-free cock proof that this in the RISC-V semantics will always enforce that policy on MMIO. Of course, I should say our model of the system is relatively limited. Specifically, we don't have asynchronous interrupts. We have a basic MMIO and a sort of, I think, currently a fixed memory layout with some RAM and some MMIO, and that's it. But all of this can be tuned. So there's an end-to-end theorem which says that we actually validate that policy on the trace of MMIO interactions, which I'm not going to explain in detail, so you have to trust me. And I want to finish with maybe some brief conclusions, and I see that I don't have much time left, so
14 seconds.
yeah, some next things I want to mention is relational verification. So we want to not just offer integrity guarantees, also confidentiality, and look at specs for side channels. Apart from that, we want to improve the tools, and we are considering to look at real systems, where we have very small and minimal trusted code interacting with a big untrusted system, and apply this machinery to that setting. And that's it.
One question.
So there's an obvious thing that you could try to apply what you presented in this talk to, which is the previous talk. What is stopping you from redoing automatically everything they did?
That's a very good question, and in fact, we are in another project. We are still working with the series code base. I've been tempted to migrate that work to just using minimal caps and Katamaran, but for sort of historic accident reasons, we're not doing that at the moment. But I think it might be a good idea.
But do you expect that it would just automatically work, or do you expect that there'll be something that will not work?
So I haven't had time to think about it in detail, but I think in most it should work automatically for most purposes, yes. It's a very different way of reasoning. If you're used to Iris and you have to switch to doing this symbolic execution based reasoning, it's quite different. So, yeah.
Okay, tea time.